Hello everybody, we started with 8080 instruction set in the part 1 and part 2. We'll continue with the instruction sets here in this class also. So we started with data transfer instructions, and we have already seen move, in, out, LEA and flag transfer, data transfer instructions. And today what we are going to see is something known as string data transfer operations. Okay, string means it allows multiple data transfer operations, right? And it is within the memory location. Okay, so suppose you have an some set of data. Okay, it could be 100, 200 in memory location. If you have to take this data again, put into some other memory locations, so not only a single word but a set of words. Okay, there could be some 100 bytes or 100 words, whatever the case may be. You have to bring this data as it is from this memory location to some other memory location. So that is possible using, instead of writing each instruction one at a time and putting it into a loop, we have a simple method of doing it, and which is known as string data transfers. Okay, it is from memory to memory. Okay, although some registers will be used in between, right, now that we will see, but otherwise effectively this is a memory to memory transfer, right? So there are several string operations. So today we'll discuss these three. Okay, these three because these are pure data transfer instructions, and we'll see how string operations are done in data transfer, and subsequently when we learn about the arithmetic operations and logical operations, then we will see the corresponding string operations in these two, compare and the scan string operations later on. Okay, so today we'll focus on these three instructions. Right now, when we say we have to do a bulk transfer, so we are going to use this move S. Right, instead of move S. So this S stands for a string operation. So what it does is you don't have to, when you write a moves instruction, so you don't have to write the source and the destination, because it is implied. How is it implied? So the data from where this data will be fetched, okay, from where the copy is to be done, will be given by a DS and SI. So you have to preload DS and SI registers. Okay, and where the data is going to be, so this is corresponding to some memory location, say M1. The data will be fetched from here, and obviously it will be moved to this destination, right? So this is M2. Okay, although in the like physically we know that memory to memory location is not permitted, but internally when we give this command, okay, we don't have to bother. The microprocessor is going to use some internal register, mostly the accumulator, to fetch this data from this location and then put this data into that location. So that will be done. We don't have to bother what internal registers the microprocessor is going to use. Okay, now and also what it does is, after fetching this data and pushing this data into the second memory location given by this address. Okay, so obviously DS, the physical address will be DS into 10 hexadecimal, right, plus SI. Okay, that's how the physical address is going to be computed. Similarly this, right? Now if it is within the same data segment, and so suppose the 1000 is the DS, and here also you want to just push this data from say 1001 to starting from 1020. You don't want to change this 1000. In that case, you need to initialize ES also by the same value, right? So these are two different registers, but you can initialize these two with the same value also, if you want, right? If you just want a small offset between these two, right? So that can be done. So you can, so there is nothing which prevents us to put the same value in DS and ES. But while using this move command, the microprocessor is going to use a DS as an for DS and SI to compute the source memory location, and it is going to use the data available in ES and DI to compute the destination memory location, right? And after doing this, the SI SI and DI, either it will be automatically incremented or decremented based on the D flag. So when we learnt about the flag register, we learnt there is a D bit, D flag, and if D is 0, then SI and DI, after fetching this data from here and pushing the data back to this, SI and DI will be auto incremented if D is equal to 0. So you don't have to write a separate instruction to increase SI and DI. Okay, and similarly, if D is equal to 1, SI and DI will be decremented by 1. Okay, and it will stop here, right? But if you have to do multiple times, like the first from here, from the first data has been brought and put it into the first memory location, and now this has been made ready for the next data. Now if that has to go, then you need to specify how many times this has to repeat, right? So for that we need to use the rep command. Okay, so once I write the rep command, rep move, okay, that I'm going to show you an example, things will be clear. Once I write the rep command, rep move, it will auto increment or decrement, then get the second data, then go to the third data. Okay, both the source and the destination address will be auto incremented or auto decremented, right? So it will keep happening like that. So how many times it should do, so that we can specify by putting the using the C register. So that is known as the counter register. So you can initially load it with the required count. Okay, so a loop will be stopped when C becomes 0, right? So initially you need to put how many whatever is the data length, okay, a number of data which requires to be transferred. So that count needs to be put into the C register, and after the loop will be stopped automatically. Okay, obviously in not 80, 86, 83, 86 and all, where it can handle 32 bit. So you have instead of DI and SI, you have EDI and ESI registers. So this is the flag register which I mentioned. This is the in the flag register you have a direction flag. So if this direction flag is 0, then this will the move instruction. In the move instruction, okay, it will do an auto increment. Auto increment means both the SI and DI after doing the transfer, it will increase by 1. So how to set a D flag to 0? You can give an instruction of clear D. Okay, so that that puts a 0 into the DF direction flag. Similarly, if it is 1, okay, if DF is 1, so after every single transfer, the SI and DI registers will be increased by 1. And how to put a 1 into DF? So that can be done by writing STD, right? Store D. That is it puts the it into 1. Okay, there is a mistake out here, so let me clear that. Right, this is a STD. This is going to set the direction flag, right? So it's not a reset, but it is going to sets DF to 1, right? This is store. Clear sets it to 0. So okay, so this is what happens. Okay, so now this is the moves command. So when I say moves, I can write MOVSB. That means 1 byte of information will be transferred from memory location A to memory location B. I can write a MOVSW, then in which a word will be transferred. And obviously, since a word is being transferred, the SI and DI will be auto incremented or decremented by 2. Okay, and I can write also MOVSD, that is double word. In that case, SI and DI will be incremented or decremented by 4. Okay, and now when I write moves along with rep, then along with this auto increment and decrement, C is decremented by 1. Okay, C is never incremented, it is always decremented. So you have to give how many over times you want to repeat the instruction. That is initially put in C. and every time C will once this data transfer happens after SI DI increment or decrement, even C is decremented, right? But when C is decremented, it also affects the flag, and based on that, if it encounters an 0, then the repeat instruction will be stopped, right? So here this is what it does. Right, so this is an example. First, we will see how to copy a block of 100 bytes of information from one memory area to another memory area. Okay, and using just the move. And then you see this is the long program which we need to write, and subsequently we'll see once we use moves how does it simplify this long program. Okay, so essentially, finally, the 8086 might do all these steps. Okay, even though it may not appear in the software which we are writing. Okay, because we know that memory to memory direct transfer hardware wise it's not possible. Okay, only thing is this MOVS command makes programming easy. Okay, but hardware wise it will take that much more number of cycles, and it might do all these instructions. Okay, so now if I have to move this data, so initially in the program I have given array 1 data byte. Okay, so the DB indicates a data byte, so that these many datas are available. Okay, so 100 datas are available here, and array 2, this is the memory location in which these so assuming both are DS, so you have to preload ES also with the DS. Okay, because the destination address here if I just DI. Okay, so the destination address is also going to be computed as an in this case, so it is going to be computed at DS. So when we use a move command, MOVS command, then ES also needs to be initialized with the same value of DS. Okay, for this particular example. Okay, now you have this data out here. So since it is 100 bytes, so I need to first initialize a counter. So this is counter is 64H. So 64H in hexadecimal is 100, right? Or you could just write 100 here. So LEL, we saw this LEA commands in the previous class. So effective address array 1. So this memory, whatever the when we write a high level program, when I write and declare here as array 1, so some address will be assigned by the compiler, right? So that address and corresponding to that address which the compiler has reserved will be pushed into SI, and array 2 is the destination. Okay, here why I write 100 dupe 0 is all that 100 consecutive memory locations, and will have a 0 data. Okay, and it will reserve that much space. Okay, so that is the reason I need to write this, so that much memory space is reserved and initialized with 0. Okay, so that is done here. Now LADI brings this memory address out here. Now what I need to do is move ALSI. So this address is brought here, and in the destination I get into from here, from the first memory location. Okay, this data will be brought into the AL register, and when I write move DI, if the same data from AL is going to be pushed into the second memory location defined by DI, right? So array 2. So array 2. So this first data from here. Now I have to take the second data and push it into the second memory location in this array. So I need to increase SI, I need to increase DI and go to loop next. Okay, so it will go here. So what does loop do? Before jumping here, it will check the counter value, right? If it is counter is 0, if it is not 0, it will go here. So since I have loaded the counter with an 64, so it will keep doing it. So after 64 operations, right, this will go to 0, and then it will stop, and then it will come out of the loop. So this is using a simple move instruction. Now if I have to move use the instruction MOVSB, okay, what do I do? So if I have to use a MOVSB command, so I initialize this same way. I put array 1 address in SY and array 2 SD, and then clear D. Now why do I have to write clear D? Because in a MOVSB command I need to specify whether SI and DI needs to be incremented. Okay, so I can write MOVSB, so clear D. So what does this, and then a loop next. Okay, so now obviously these two instructions, increment SI and DI, need not be written because move is going to do automatically, but additionally initially I have to clear. Okay, so this additional instruction has come, and the increment SI and DI instructions are no more required here. Okay, so this is using just the MOVSB. The same program can be written in this manner. Right now, if I want to further simplify it, now what I can do is I can use the repeat MOVSB. Right, once I write a repeat SB, then this loop which I did, that also need not. So a loop is implicit in this repeat, so it will repeat it 64 times, right? 64 hexadecimal. That means 100 bytes of data will be transferred automatically, right? So now here only thing you need to remember here is, right, this is DS SI, and this is ES and SI, right? So but if you want this to be the same, then initially you need to initialize this accordingly. Okay, so that you can do that. Sorry, this is going to be DI destination. So that's how. So now you see this has become a pretty simple operation. Right now, you can, since it is it's 100 bytes of information, you can further probably simplify it by writing a word transfer. Right, here it is MOVSB. Here you can write word also. In that case, this counter can be initialized by 32H. Okay, because it is just 50, right? So this and now the thing is, this can make the operation faster, because we know that one word can also, because 8086 has got, right, 16 data lines, right? So this can act 2 times faster, because all the 16 data lines will be activated in one go. So obviously this can this will work much faster, twice as fast as this operation, right? If you are going to use S word MOVSW, that's moves word, so you can do that also, right? And then suppose you want to start from the last from the last to the last, and then second last to the second last, and then finally come to the first and first, you can do that also. So in that case, again, the number of times this remains same. So initially you need to write the ending address of both SI. So whatever is array 1, array 2 plus 63 plus 99. Okay, so that needs to be put, and here the difference is now you are storing into D. That means a D flag has been set to 1, so it will do auto decrement. Okay, so here, right, here it is just array 1, array 2 and clear D flag, whereas here it is plus 63, right? So this is going to the highest memory locations, both SI and DI, and then you are doing it in the reverse direction, and hence you are setting the direction flag to 1. So this will again repeat 100 times, and then obviously you can write MOVSW, and you can write this as 32H for a faster data transfer. Okay, so this is 1, 2. Now let's see. Now suppose you have to reverse the order. That means you are taking the first data from this source and putting it into the last one. You are taking the second one and then putting it to the second last one. So you are moving from high to low here, and here from low to high. If you have to do a reverse order setting. Okay, so if that is to be done, then you can just modify this like this, okay, the count remains 32, SI you are bringing array 1. In the DI you are taking the last location. Okay, so that is it. Clear D is going to increase it every no, so it is going to be the incrementing order, right? So MOVSB. Now what MOVSB does is, since this is 0, it is going to increase SI by 1, and you are increasing DI also by 1. But actually I want it in the reverse direction, and I have taken a DI as the last memory location. I need, and it has gone +1, but I required -1, so I can do subtract DI -2. So obviously this will bring it to -2 out here, and then I can write a loop command, right? So it will keep doing. Now I can't use rep here, right, in this case, because it is a reverse order, and I need to modify the value of a DI, so I need to use a loop. Okay, so this will start decreasing the data. Now again, if I have to make this a little more efficient, I can probably write 32, right? So this will go to 32H. So only in 52, this remains like this, this remains like this, but obviously this will change, correct? Now how much should it change? Just think over it, right? Because it's an word, right? It's an MOVSW we are writing, right? So it is going to increase it by 2, right? It is going to increase it by 2, right? I want -1, right? So what is this? What it should be? Whether it should be DI subtraction 3 or 1 or 4? Just think over it. So this will accordingly get changed if this is 32 and this is SW. Okay, so that is that is way, and for more examples you can refer to the tutorials which we have as a separate course, right? You can go to my web page, and tutorials, there is a course on microprocessor tutorials, okay, in which more number of problems have been explained, so you could refer to that, right? And then we have the load right here. Now in the load, as compared to the moves, okay, one of the the source is already specified here. The destination is fixed. Okay, if it is a byte, it will come to AL. If it is a word, it will come to AX, and if it is a double word, it will come to EAX. Okay, so in the load command is very similar to the MOVS command. Okay, only thing is here in the MOVS command, the destination is given by DI and ES, whereas in the load, the destination is fixed. Okay, you don't have to specify this destination. Okay, it is AL, AX or EAX. So after the load, again SI will be incremented or decremented. So there is no DI here. Okay, DI doesn't play any role because it is every time this data will be brought. So if you just put it into repeat or something like that, then whatever is the data in AL will be overwritten. Okay, so you have to, so depending on the application, you have to see that. Okay, if you are bringing it into AL and you want to do some operations and all, no, you need to move that out from AL and do some operations and store it elsewhere. Otherwise, AL will be rewritten. If you just do rep LODSB, then it will be overwritten every time. Okay, so every time it will be brought to AL, AX or EX. Okay, so if it is a W, then SI will be auto decremented, and it will be if it is a double word, it will be done by 4. Okay, again for all this the flags are not affected. Okay, because this is a data transfer instruction. And also again, whether this SI, whether it will be auto incremented or decremented, that depends on the flag. So we can use the clear flag or the store clear D and CLD or STD commands to set the flag to 0 or 1, and accordingly it will be auto incremented or auto decremented. Right. So this is one load S. So what it is doing, it is computing the physical address, okay, from ESI and DS. So in 86 it will be SI and DS together. This is the memory location. So this is the lower memory location. Since I am using a word, so this lower one is being brought into the AL register, and the higher bit, okay, the next from the next memory location, what A0 is there, so that will be brought into the AH register. Okay, so this is how it works. Yeah, the store command and a store S, store byte or store word is very similar to load. Here the source would be AL register, AX register, or EAX register, depending on whether it is SB, SW, or a store double word, right? If it is an and the destination address will be given by ES and DI. Okay, obviously ES into 10 hexadecimal plus DI is the offset. So this is the destination index. So the physical address will be of the memory will be accordingly computed. So whatever data is available in AL, AX, or EAX, depending on what instruction you have given, that gets gets loaded, right? So if I give a store SB, okay, strong string byte, so 1 byte of information from AL register will go to the address specified by ESDI, and DI will get an incremented or decremented by 1 depending on the flag, right? Sorry. Similarly, if I write in a store SW, then the data available in AX register, because it's word now, so whatever data is available in the AX register, it's 2 bytes of information will be transferred to the memory location specified by ESDI, and DI will be auto incremented or decremented by 2. And finally, we have a store double word in which the data available in EAX register will be transferred to this memory location, right? And then DI will be auto incremented and decremented by 4. Like in all the string operations which we learned, this whether it would increase or decrease, that depends on the direction flag. So we need to use the clear D or the store D commands to set the direction of the DI, whether it has to increase or decrease. And like all other data transfer instructions, flags are not affected by the store S commands. Okay, so this is just one example of what about the store S. What we are doing is we want to fill 100 memory locations. Okay, this is the displacement, and starting from here, okay, for 100 memory locations, we want to fill with F6H. Okay, this data. So this is like DAT1 and 100 bytes of locations, right? They have been inserted with, you can write 100 duplicates, 100 times it is going to duplicate. Okay, this is just reserving that much of space. Okay, when I put question mark, I think whatever is the previous data, it will be retained. Whereas here, if you see 0, when I write 0, that means in those 100, those 100 will be reserved. Okay, not only it will be reserved, that those memory locations, you will have a data return 0. Okay, whereas if I write a question mark like this, 100 bytes of memory locations will be reserved, but as whatever was the previous data available there, you don't bother about it, it remains as it is. Okay, so you could do that. Now, so there will be certain advantage in writing 0. Okay, so now I write start. So move DI offset, so that this particular DAT1, okay, that offset has been brought to DI, and I want to write this data into each and every location. So into AL I get this data, and in CX I load 64, which is 100. Okay, and I write a clear D, and then I write a repeat. Right, so every time first in the first location whose offset is given by DAT1, and value of 0 F6 will be returned, and again right, since it's an store operation, automatically it will, and then I have written clear D, so obviously it will automatically increase the DI value by 1, and then again keep repeating it till the CX value comes to 0. right? So and every time this repeat happens, the value of Cx will be automatically decremented. So this can be done. Again, to make this entire thing a bit more faster, I can if I have to write this value, right? So I can write okay into AH, okay, 0 F6 and F6, right? I can do that. Let me write it more clearly. Instead of this, I can write instead of AL, I can write AH, and then I can write F6 and F6, right? So this becomes a word now. Since I have to write F6 F6 everywhere, and this I can bring it down to 32. Right. Again, the advantage, like I said, 8086 has got 16 data lines. So 2 bytes of information parallelly it can be brought. So the number of cycles required will reduce by half if you do this. Okay, so that can be done. Okay, so we'll stop it out here. And there are 2 more instructions, data transfer instructions, string operations, which is ins and outs, which we will see in the next class. Okay, thanks a lot.